Okay, so we're going to talk about limits of infinity. And so what we're really looking is as x approaches infinity. So on a graph, the idea is you want to look at what the far right, and as x approaches negative infinity, what the far left side y values of the graph are doing, okay? And because we're looking at extreme values, what we're really doing is comparing the rate at which the numerator and denominator grow. So typically these problems are all going to be rational functions. So you'll see it written as one or the other, not both. And you're going to have some function on top, the numerator, and a function in the denominator, okay? And so you're comparing those rates of growth. Last year in secondary 3, you would have referred to these as horizontal asymptotes, okay? This year, horizontal asymptotes are the same theoretical idea behind limits of infinity. So there are 3 rules to memorize, okay? And they have to do with finding the highest power, okay? Highest exponents only. So the first scenario that's easiest for students to remember is what happens if my numerator exponent is the same as my denominator? Well, what that would look like is, let's just say we're going to infinity, and I'm going to have 5x3 squared plus 1 all over 6x squared plus x minus 10. So as we're plugging in 10, and then we're plugging in 100, 1,000, a million, a trillion, what happens is these smaller numbers all become insignificant. They don't really affect the overall highest power term, okay? So since these are both growing at the same rate, essentially, we're just looking at the coefficients. So that's our rule. Use coefficients. All right, so let's see. What else could happen? Well, the second one for students to memorize is what happens if my numerator exponent is smaller than my denominator. So something like 5x over 3x squared, okay? Well, as we're plugging in 10, 100, 1,000, a million, these values are always going to be smaller than these, and since these are being squared, they grow at a faster rate. So we have a really small number over a larger and larger and larger number. And so theoretically, these values are going to be so small that they will approach 0. Whether it's positive or negative side, it doesn't matter. They're closer and closer and closer to 0. So that's your answer. Not y, it's our limit, 0, okay? Y equals 0 would be the asymptote. The limit value is 0. And the last scenario that's harder for students because it's more complicated is what happens if my numerator exponent is larger than my denominator. So same idea. What if we flipped these? I'm going to put both of these back on. Well, we'd have a larger number on top over a smaller number. Last year, you found out that these were slant asymptotes. So your values don't verge on one value. They keep growing larger or smaller. So we don't really have an asymptote, but we want to know what the limit value is. And so it's either going to be positive or negative infinity, but you need to use the powers. Depending on your limit, you're going to substitute either x equals positive 1 if you're going to positive infinity, or negative 1 if you're going to negative infinity. And then you need to use the coefficients of the highest term. Coefficient. I can't talk and write. Okay? So that one is a little more complicated. It's not really that much longer to do, though, once you get used to it. All right? So let's try some examples. So let's look at example number 1. So I want to look at my highest power. So, and they're not always written in order. We've got that one and that one. So since those are both x cubed, they're growing at the same rate, and so we use the coefficients. You don't have to explain or write any justification or anything at all, okay? All right, example number 2. Now, we're going to ignore this 1. So really, if I write this as a power, I'd have x to the 1/2. And remember, mathematically, I know you're not allowed just to cross out that 1, but this is as we're plugging in larger and larger and larger numbers, that 1 becomes insignificant, okay? And if you want, you can even put a negative here, because technically it is still there. and this would be x to the first. So I've got my numerator is smaller than my denominator, and so I know my y limit is going to be 0. There would be domain restrictions, but that's why it's minus x, and we're plugging in negative infinity, so the domain restriction does not apply. That usually doesn't come into play with limits of infinity, okay? All right, the next one, we've got the highest power. Notice how I circle the negative with the 3. So we're going to infinity. I know I'm larger on top, so my choices are positive infinity or negative infinity, okay? So at least narrow down if it's multiple choice. So I want to plug in, if I'm going to positive infinity, I want to plug in a 1. And I just want to find out if this is going to be positive or negative. So I'd have a positive on top, cube that positive times a negative, and so we're going to get negative infinity, okay? And like I said, there were 3 criteria we had to check, but the work doesn't take that much longer. All right, let's look at number 4. We're going to negative infinity, and we're looking at the square root of x squared all over 2x. Now, I'm going to put this in quotes. We can't really take the square root of this x squared because there's other terms after it. So I'm going to put it after in quotes, like, because this is like fake simplifying. The square root of x squared is x, okay? And then we've got over 2x. Now, what you'll notice is that the powers are the same, okay? So same powers. So they are going to be equal, but what we had to also recognize is that when we had the original problem, it was a number being squared. So this is always going to be positive. All right, so you want to kind of apply any like fake math or theory that you're doing as part of your answer, because sometimes it will make a difference. So we've got this one, it won't because it was already positive anyway. We've got 1 over 2. We're still using our coefficients, and we're just really theoretically applying their rate of growth. They're growing at the same rate. All right. So let's look at the next one. Now, this one's kind of different because we have an exponential power function on the denominator and a linear in the numerator. So I can't really talk about their powers the same way. But remember, a linear function has the same rate of growth. Exponential grows really, really, really faster. So what we know is that e to the x is always going to grow faster than x. All right? And so because it's always larger on bottom, our limit value is going to approach 0. Okay? So same idea here. This time, though, we have e to the x over e to the x. Those are the same functions. So they're going to have the same rate of growth. So use their coefficients, and we get 1. All right? So I have some for you to practice. See how you do. There might be some cleaning up to do. I threw in a little curveballs on you, but read your comments and I will help you more there too, okay? All right, good luck.